Hello, my name is Rob Reynolds. Welcome to Business Calculus section 1.5. Today we're going to talk more about limits. And the main thing about limits is it's about the journey, not the destination. And what I mean by that is as you approach something from the left, or a function from the left and from the right, if they approach the same thing, then the limit exists. Even if even if that destination is an open dot and undefined. It's about the approach. It's not about this particular point. So limits of functions, we're going to find limits graphically by kind of what I just showed you there. We're going to look at the definition of the limit, and then we're going to learn how to evaluate limits using algebra. So again, let's go back to some graphics. The first thing, if I just ask for evaluating the function at 1, you go to the x value and you say at 1, the function is defined at 3. And f at 2, even though there's no dot there, it also looks like it's at 3. I could even ask for f of 0, and you can see that's a point, 0, 1. So there's your x, f of x, which is your y value. But if I ask for the limit, then I'm looking for the left approach and the right approach. Well, the left approach, so we can say the limit as x approaches 2 from the left, that's what this little negative is, of this function is 2. But the limit as x approaches 2 from the right, coming this direction, is 4. And since the limit from the left does not equal the limit from the right, then we say this does not exist. Here are some other examples. You can pause the video and see if you get these answers correct. I just added this slide, so I don't believe it's on the PDF handout, or it could be a Word document handout, that if you go to Blackboard, you can follow along with this video and actually work out some problems with me. Remember, this is not a spectator sport, so you learn mathematics by writing and doing, and so I prefer that you treat this like a face-to-face class, and you're actually working the problems with me instead of just watching a video. F at 0 is undefined. It does not exist. Sometimes we use the null set there. F at 2 is 0, and f at 3, even though the left approach and the right approach, f at 3 is 3. The function does exist. So now I'm not going to talk about the function, I'm going to talk about the approach. The approach from 0, from the left, looks like maybe negative infinity. The approach, but wait a minute, the approach from the left, yeah, is negative infinity. Oh, now they just asked for the limit. So now I'm going to look, does the left approach equal the right approach? And that does not exist. Usually I prefer does not exist. This is just approaching 3 from the right. So here's the right side, and the limit is 1. And then I will ask again, does the limit from the left equal the limit from the right? Well, the limit as x approaches 3 from the left, oops, did I do that wrong? I did. Here's the right side. Oh my goodness. Let me back that up. This from the right is a 2. From the left is a 1. And since 2 doesn't equal 1, this does not exist. And then this last one is looking as x approaches negative infinity, which is way out here, way to the left. And it looks like the limit is 1. The y value is the limit. So the definition of a limit is the limit as x approaches some value c, and c here would equal 1. It's some x value of the function equals L, which is the y value. So in this case, the limit as x approaches 1, well, as long as it's from the left and the right, then I would say f of x is equal to this one. You can think about limits as what it approaches. It's not what it's at, but it's approaching some value. So again, this is just more notation. and the word approaches is the important part. Then algebraically, we can do direct substitution as one method to evaluate limits. So you can simply just do 1 squared plus 1 and end up with the answer 2. It's as simple as that. You could do a table setup using your calculator and just look at the left approach and the right approach. But if you know that it's a polynomial, which is continuous, smooth, no gaps, no holes, then you could just do direct substitution. For example 2, part A, you could factor this thing. It's called the difference of two squares. So x plus 1 and x minus 1 divided by x minus 1. Why wouldn't I evaluate the limit as x approaches 1 from the get-go? Well, because if you were to throw in a 1 here, you got 1 minus 1 in the denominator, and that's not good because you can't divide by 0. But now the new problem says the limit as x approaches 1 after you cancel this x plus 1, and then you could do direct substitution and just get a 1. For part B, again, if you don't know how to handle something, you could go back and just look at the graph of this thing. So you could pull out your graphing calculator and identify that it looks something like this. And again, it's the limit as x approaches 1. So I'm going to find 1 here, and then I'm looking at the left approach and the right approach, and this does not exist. There's other ways to do that, but maybe just looking at the graph would be the best. Again, here I'm looking as x approaches 1 of this function of f of x. Well, as it approaches 1, it says as x equals 1, it's at 0. X equals 1. For all other values, y equals x. So if you look at the graph of y equals x, it's just a 45-degree angle line here. This is x and this is y. And so 0, 0 was already a point on this, but it says, well, at 1, it's at 0. So there must be a hole right in here, an open dot right here, and then it jumps down here. So again, the graph of this is kind of important, but I'm not interested in where the function is or what the y value is when x is 1, because if I ask f at 1, then you would say 0. But if I say, what's the limit? The limit's looking here, and when x is 1, y is 1. Again, you're welcome to go and look at the PDF file, worked out solutions. Again, it's about the journey, not the destination. So it's about the approach from the left and from the right. So example number 2, I did a quick graph. I could have done a table setup using your calculator, and I need to show you how to do that as well. And I'm going to do that for example 2B. So again, this Lindsay Lohan, I don't know if you've seen this movie or not, but she talks about the definition of a limit. She's a little bit off on her definition. I believe she says something like if the limit doesn't approach anything. And so we're not going to talk about it. And I understand what she means, and she's the writers who tell her what to say. I'm not dissing on Lindsay Lohan, but it's really not that it doesn't approach anything. It's that it doesn't approach the same thing. So you're looking at the left approach and you're looking at the right approach. And if they don't approach the same thing, then you say the limit does not exist. And again, you can confirm that with your table setup, again, from part B. And I'll just show you how to type that in real quick to get a table setup so you can do this as well. First thing I want you to do is hit your y equals and clear out any functions you may have had in there. To type in a fraction, I'd really recommend hitting second y equals and then press enter, and that will give you a fraction key, so you don't have to worry about encasing the numerator in parentheses and the denominator in parentheses. To find absolute value, it's under math, right arrow to numbers, and then if you just, it's number 1, you can just press enter. So that gives you the absolute value. X is below the mode, x minus 1, arrow down for the denominator, which is another x minus 1. And then, well, I'll hit zoom 6 to give you a standard, but I'm not really interested in what the graph looks like. I'm more interested in the table setup. So you could try to hit second graph, which is a quick table setup, and you could change the values of these, but the x values, if you need to see something closer, by hitting second window. And some students even like to use the ask especially when they're asking for certain values. Then if you hit second table, you can just generate any kind of table in your homework on WebAssign. They might ask, what is it when it's if you let x be 0.9, and you can see it generated the -1 and then 0.99, because that didn't show up in my table before. So 0.999, and so you can enter values, and you can see it's getting really, really close. From the left, it's getting close to 1, and then you can check some values to the right by checking 1.001. Now, keep in mind, 1.001. Keep in mind that these look like a 1, but when you actually go up here and highlight this thing, the y value, well, yeah, this is a bad example, but sometimes you have to highlight it's just, the graph of this really is 1 in both directions, because that's what the graph of part B looked like. It's always a 1 from the left and the right. But sometimes you have to highlight that y value to actually find the exact coordinates, the exact y value. Your calculator will round it to a 1, but you want to look down in this area because it might be 1.00001, so it might be really close, but that's not even the point, because the point is it's approaching 1. Here it's actually at 1, but I should show you another example where it's approaching. So far, the definition of a limit is a function and property of limits. The definition of that limit is if it approaches from the left and the right. If it's the same, then it exists. If it's different, then it does not exist. And it must be continuous for the limit to exist. No holes, no gaps. So if it is continuous, no holes, and it's a polynomial, then we can just do direct substitution as one method for evaluating limits. Limits are really nice. You can multiply them, you can add them, you can divide them in any order. You can do exponents and radicals with limits. It's hard to mess up limits. So again, you can pause the video here before I reveal these, but you can check to see if you get the correct answers for these. And what this is saying is this is the limit as x approaches 2 of the function. And they're telling me the function here is 3. So if you look at the graph of just y equals 3, I'm asking what's the limit as x approaches 2? Well, the limit from the left and from the right would be that 3. So again, pause the video and see if you can answer these just by direct substitution. And there are solutions. In example number 4, I see a nice polynomial. So again, direct substitution is the name of the game so far. There are other techniques, but in this case, I think direct substitution is working quite fine. So that was the first technique that I would always try, is direct substitution. And you actually applied a limit property, which I said properties are really nice. You're distributing, you're actually just taking the limit of each one of those things, but you don't need to show me all that work. Another property of limits is instead of thinking about evaluating the 2 into this whole thing, you can just find the limit of this little guy and then raise it to the 4th at the end. That'll save some time with mathematics. Again, it's almost impossible to do anything wrong with limits. Unlike logarithms, boy, a lot of property problems with logarithmic functions, but limits are going to be fine. If direct substitution cannot work, and I'll show you some examples of that, then we're going to try factoring and conjugate. And then the last technique would be your table, to go to your graphing calculator and look at that table setup, and I'll try to show you another example of that because the previous one wasn't the best example. So you do need to know how to factor, and I've learned in teaching this course several times that it's a good idea to review some of the techniques or different types of factoring. So we could pull out the GCF because I see each has an x and each is divisible by 2. So taking half of everything And well, literally, it was what I'm thinking is when you pull out a GCF, I'm really just thinking divide each term by 2x. So x squared minus 4x plus 8. Here, this is called the difference of two squares. There's no GCF because I got an x and a y, but 3 times 3 is the 9. X times x is x squared minus 5y gives me, and a 5y over here gives me the 25. But then difference of two squares, this is a plus. Trinomials, there's all sorts of types of trinomials, but the way that I teach is you're looking for factors of 12 that differ by, because this is a minus, 4, and factors of 12 that differ by 4 are 6 and 2. Signs are going to be different, so one's a plus, one's a minus, and this tells me what the larger term is. So the larger here is plus, that's a negative. So that way when you do your outer and your inner terms, we'll actually get a positive 4x, and you can just check it real quick, your outer and inner terms. Your outer terms is negative 2x, your inner terms is 6x, and certainly that gives me the 4x that I was looking for. The greatest common factor, factor by grouping, usually you take the first two terms, but I see a hint here, the GCF. So what's the GCF of this guy? 3y squared, leaving me with another, no, not 3y squared, just leaving me with y squared. There's the 3y. Now, you've got to get another, if I write down y squared plus 3y, to factor by grouping, messing that up. To factor by grouping, you really do need to work on getting another factor, y squared plus 3y. Otherwise, you cannot. So the goal is thinking about what can I factor out of this guy to also get this common factor, y squared. And so there's something that goes in this blank so that when I multiply by y squared, I get this guy, and I think it's negative 6y. But then I want to check negative 6y times the 3y gives me this thing squared. So I see my mistake. This should have been just a y. Checking this term, 3y squared times 3 gives me the 9y squared, and I shouldn't have put it in this extra y here. But I found it because that negative 18y, the last term, didn't work out either. So now it does work. Negative 6y times the positive 3 does give me the negative 18. So then I can pull out a y squared plus 3, leaving me with 3y squared minus 6y. And boy, did I not follow the directions because it said GCF first, but I can do the GCF last. This would have been an easier problem if I would have pulled out the GCF, which was what? I didn't follow my own directions. Pull out a 3y, leaving me with y minus 2. So final answer, and you can multiply these in any order. The last thing that happens is factoring by cubes. We'll call this problem A and this problem B. For problem A, the rule states for factoring cubes is you write down the basis of what's being cubed. So x is being cubed, and 2 cubed gives me that 8. So I'll say x and 2 are the bases. Then the rule says square the first base, take the product of the bases, square the last base. First you keep this original sign, then you change it, and the last one's always plus. For part B, I would try GCF first, but there is no GCF between 8 and 27. So again, I would think about what are the bases? What's being cubed? What can I put into this pink spot to get 8x cubed? And that pink spot, I believe, is 2x. And then likewise, I'm thinking, well, what can go into this spot and cube to give me the 27y cubed? So that blue base, what's being cubed is what? 3 cubed is 27. 3 times 3 times 3, y. So let's do the rule again. Square the first, take the product. Don't worry about them plus or minus. So I'll just say 6xy. We'll get the sign later. Square the last. Don't worry about the sign. Either way, it's going to be positive because the last one's always plus. First, you keep the sign, which looks like I already did. Then you change it, and the last one's always plus. Here's the definition of cubes. You can pause the video and write that down if you want, because you get square the first, take the product, square the last. know how to factor, I can write down the bases, square the first, take the product, square the last. First you keep the sign, then you change it. Last one's always plus. And look, since I can't evaluate direct substitution because that'll have me divide by 0, which is undefined, then I will factor first and then evaluate the limit as x approaches 1 of x squared plus x plus 1, which is just 1 plus 1 plus 1, or 3. And again, worked out solutions posted on Blackboard. Here's the illustration, and you can see that there's a hole. That's called a removable because I actually factored out or divided out that factor. So likewise up here, I'll factor this to be x plus 3, x minus 2. I'll cancel. Sorry about that. And then I'll evaluate the limit as x approaches -3 of just what's left, x minus 2. So -3 minus 2 is -5. So again, factorings are a great technique. You can check out Blackboard, the PDF worked out solutions. Rationalizing, again, direct substitution is not going to work, and I don't know how to factor that thing. So rationalizing means, and you're good at rationalizing the denominator, but in calculus, oftentimes we rationalize the numerator. So rationalize means change that middle sign. So I'm going to multiply the numerator and denominator by 1. Really, it's just I'm multiplying this yellow fraction by a unique value of 1. So this blue number, any number divided by itself, is 1. So I'm not going to change the yellow fraction value because I'm just multiplying by a blue 1. It's going to change colors, but it's going to be equivalent. So my new, I'll change colors for you. My new limit after I multiply this together, which will be equivalent to the yellow, is x plus 1 minus 1 over x times the square root of x plus 1 in parentheses, which is x over x times this junk. And then I can cancel. So it's really just the limit as x approaches 0. And all I have is a 1, because when they cancel, any number divided by itself is just, so it's 1 divided by the square root of x plus 1. And when I throw in a 0 there, I get 1 over the square root of 1 plus 1, or 1 over 2. That was your first look at rationalizing. And again, worked out solutions are posted. If I'm going too fast on this video, you're certainly welcome. Did I get 1/2 as a solution? Yes, I did. Good. I was thinking the author got a different solution, so I might have made a mistake. All right, so one-sided limits. I talked to you at the beginning of the video a little bit about this. This is the left, this is the right. And if you don't have a graph, then you could pick up your graphing calculator and actually graph this thing. But with a graph, you can look. The left-hand limit, the limit as x approaches 0 from the left, looks to be around -2. That's this guy. So that, remember, the limit, I'm just looking for what this y value is. As it approaches 0. I don't care about what it's at. And the limit as x approaches 0, this is so sloppy. I'm having a hard time even understanding it myself. So this is x approaches 0 from the left, approaches 0 from the right. And from the right, here's the right, but it looks like it's a +2. So by the way, if I were to ask what's the limit as x approaches 0, Lindsay Lohan would say it does not exist because the limit from the left does not equal the limit from the right. So there's, again, worked out solutions. This says all the values of x that are less than, so that's from the left. This is from the right. So we're just going to do direct substitution. The limit as x approaches 1 from the left of this would be 3, and the limit as x approaches 1 from the right of the other function, the 4x minus x squared, is also 3. So again, the limit exists. You can pause the video if you'd like. Here's another example. It looks like they're asking for the limit. It's the limit from the left and the limit from the right. So the limit of 2 from the left looks like 20, and the limit of x approaches 2 from the right looks like around 22. So that's why they're saying the limit does not exist. Here's a stair-step piecewise function. Unbounded just means it goes to infinity. Lindsay Lohan would say, well, the limit doesn't exist, but maybe the left hand and the right hand limits do. So the limit from the left would be negative infinity. The limit from the right would be positive infinity. So again, if you try direct substitution here, you're going to divide by 0, so that's no good. So you could do this. You could look at the graph of this, and if you knew that there's a vertical asymptote at x equals 2, and you knew that the function then did this hyperbola, you can just look at the function and see what's happening from the left and what's happening from the right. But I wanted to show you, you could certainly do this on your graphing calculator again, and graph the function, which a table setup is a valid method, but again, this is like at last resort to try to evaluate these things. But I'd go to table setup and start at negative, well, we want it to approach 2, right? Not negative 2. So I'm going to start the table at 2, and it doesn't matter what you're going to go by increments of, because we're going to ask it specific questions. Like, what about, oh, it's already in there, 1.999. So it looks like I'm asking about 2's, but I'm really asking for about 1.999, and I'm asking for 2.001. So 1.99 is from the left, and that's a big, massive number. And if you highlight it, you can see negative, I don't know, 3 million. And then this is even a bigger number, which who cares? That's just there. So this is a negative big number, and this is a positive big number. So I would say the limit as x approaches 2 from the left is a negative big number. We'll say negative infinity, and the limit as x approaches 2 from the right is positive infinity. You can see that over here. This is going to positive infinity. This goes to negative infinity. And then so what do you do for the answer? The answer is, what's the limit of as x approaches 2? You guessed it, does not exist. And again, you can check out solutions on Blackboard. I hope this video was helpful. Email me with your questions. Thanks.